Hello everyone, my name is Chao Liang. I recently joined Sichuan University in Chengdu, China as a system professor. Before that, I was a postdoc fellow working with Liang Ampuero and Daniel Pino Muñoz in France. Today, I'd like to present my work I did during my postdoc, which is the rare occurrence of supershear earthquakes on an elongated radiant state fault. As we know, earthquakes do not occur instantaneously. They rupture at a finite speed, limited by the elastic wave speeds in the solid. Higher rupture speeds generally produce stronger directivity effect and higher slip rate, which then generate higher ground motion and more severe damage. Therefore, it is important to understand how fast does an earthquake rupture and how often does an earthquake achieve such a rupture speed. Most earthquakes rupture at a speed slower than radio wave speed, but some earthquakes rupture at even faster speeds between the shear wave and P wave speed. This phenomenon has been discovered by theoretical and numerical studies and validated by laboratory experiments and real seismic observations. The constructive alignment of shear and radio wave fronts following the supershear rupture front form a Mach front. Similar to the sonic boom following the supersonic jet plane, these Mach fronts can carry strong ground motion far away from the faults and produce severe damage. Therefore, it is important to understand how often do supershear ruptures occur and what controls that. The first supershear transition mechanism was proposed by a series of papers from Burridge and Andrews in the 70s, and that's why it's called the Burridge and Andrews mechanisms. This theory later has been improved by many other scholars. The key point from this theory is that the fault's initial stress must be sufficiently high so that the length of the daughter crack propagating ahead of the subready rupture front can continuously grow as the propagation distance increases. When the daughter crack length exceeds the critical nucleation length, the supershear transition occurs. And the initial stress on the fault is usually written in the dimensionless way, which we call the S ratio. In addition to this classic mechanism, many other mechanisms also exist, including the free surface effect, the fault stress and strength heterogeneity, fault roughness, geometric complexity, and the influence of fault damage zone. Despite the rich spectrum of mechanisms that can generate supershears, supershear ruptures are still rare in nature. And up to now, the published literature only contains about 10 supershear earthquakes. And a recently unpublished survey from some colleagues have shown that the supershear earthquakes only make less than about 15% of the large strike-slip earthquakes since the 2000s. The question is why it is so rare. The problem is what controls the physical properties, what is the physical properties that controls the rate of occurrence of supershear earthquakes. So far, most models of supershear earthquakes focus on single dynamic rupture, which is useful in exploring on what stress conditions do supershear occur. However, this type of model is incapable of evaluating how likely can such conditions be achieved over multiple earthquake cycles. On the other hand, most current earthquake cycle models assume antiplane shear or quasi-dynamic approximation, which are incapable of producing supershear earthquake sequence on large faults. Currently, there are a few fully dynamic 3D codes, but they are quite expensive computationally and less useful in exploring a wide range of parameters. Therefore, in our work, we conduct fully dynamic earthquake cycle simulation on an elongated in-plane fault governed by radiant state friction. And we also take into account the finite seismogenic width by using a 2.5D approximation, which has been shown to be a good approximation for long faults. And our code uses spectral element method on an unstructured mesh and can handle complex geometries. You're welcome to check out our implementation and source code on GitHub. And here's the setup of our model. we model earthquake sequence on a velocity weakening patch surrounded by two velocity strengthening and steadily creeping regions. The fault is loaded by a constant remote plate velocity implemented in a backslip approach. On the right, I'm showing the results of an example simulation. The middle figure shows the accumulative slip on the fault. The red curves indicate the coseismic slip, and the black curves indicate the interseismic slip. For each earthquake in the given sequence, we analyze the space-time plots of the slip rate to extract information of the dynamic rupture process, for instance, the rupture speed. We can also obtain the S ratio for each event. As you can see here, this sequence is a mixture of sub-Rayleigh and supershear events. We can also observe that the supershear events possess a lower S ratio than the sub-Rayleigh events. Now, since our model does not contain material heterogeneity, free surface, or geometric complexity, the most relevant supershear transition mechanism is the Burridge and Andrews transition mechanism, where the controlling parameter is the S ratio shown here. And here we derive an expression for the S ratio of a characteristic event. To compute the S ratio, we need the peak stress, residual stress, and the initial stress for an earthquake. Both the peak and residual stresses are given by the rate and state friction law as shown here. Now, the challenge here is to estimate the initial stress of an earthquake prior to an earthquake. In a single dynamic rupture simulation, this would be specified as an input parameter. However, in earthquake cycle simulation, the initial stresses cannot be fully controlled, but we can still obtain a rough estimate of it, and this is how it works. The initial stress can be written as a residual stress, as the residual stress from the previous earthquake plus the stress accumulated during the interseismic period, which is the stressing rate times the inter-event time. Now, for an elongated fault, the stressing rate can be written as the following. The final task now is to estimate the earthquake inter-event time, which is basically the time over which the creep inside the velocity weakening patch reaches the critical nucleation length. And this time can be estimated using the theory of earthquake nucleation. And we follow similar procedure in Catania 2019, but replacing all the relevant stress intensity factors used in her paper by the 2.5D expressions. And finally, we can obtain a formula for the S ratio. Except for a parameter alpha, which is on the order between 1 to 2, and another parameter eta introduced by the 2.5D geometry, the S ratio is primarily controlled by two dimensionless parameters, A divided by B and nucleation length divided by W. There are indeed some physical reasons why these two dimensionless parameters pop out. On one hand, if we decrease A divided by B, the direct effect is weaker, which gives a smaller difference between the peak and initial stresses. On the other hand, if we increase nucleation length divided by fault width W, we then need a longer inter-event time for the next earthquake to nucleate, and then the fault will be able to accumulate a higher initial stress from the residual stress after the previous earthquake. Both of these two effects act to lower the S ratio and eventually favor the occurrence of supershear earthquakes according to the Burridge and Andrews mechanism. And this is exactly what we see from numerical simulations. In this figure, I'm showing different rupture styles for different different nucleation lengths divided by W while fixing A divided by B. Since the real nucleation size Ln is unknown prior to the simulation, we use the 2D estimate LRA from Rubin and Ampuero 2005 paper as a proxy to set up our parametric study. It is clear that as we increase the ratio of nucleation length over the fault width, the earthquake sequence transition from a pure sub-Rayleigh events to alternating supershear and sub-Rayleigh to pure supershear event sequences. As we further increase the nucleation length, the restriction from the narrow fault width start to kick in, and the earthquake sequence becomes a mixture of weak supershear and sub-ready partial ruptures, and eventually the fault slides aseismically when the nucleation length is too long. On this map, we summarize the supershear occurrence rate and the median S ratio for the simulations we've conducted. Here we only count the sustained supershear, where the supershear rupture length is at least half of the total rupture length. The field squares are the sequence of purely sub-ready events, and the field circles are the sequences that have supershears. The crosses indicate the aseismic sequence. It is clear that there's a certain parametric space that favors supershears. In this range, the fault needs a low A divided by B value, which is less than 0.4, and a high LRA divided by W. And in this intermediate range here, only purely sub-ready events can occur. And when the nucleation length divided by W is too high, then the fault slides aseismically. On the right, I'm showing the median S ratio for different parameters. It is clear that the S ratio decreases either when decreasing A divided by B or increasing the nucleation length divided by W, which is consistent with our theoretical estimates. Finally, we also look at the supershear transition distance from our simulation. From the left figure, we have two key findings. The supershear does not occur when S ratio is above a certain threshold, and this threshold is around 0.9 in our simulation. We also find that lower S ratio results in shortened transition distance and thus favors the occurrence of supershear earthquakes. And these observations are qualitatively consistent with the theory of Dunham 2007. However, our results deviate from the exact theoretical estimates in the Dunham paper due to the large procession size and nucleation size compared to the fault width. And in this limit, the linear fracture mechanics is not valid anymore. On the right figure, I'm showing we also show that despite we tested faults with aspect ratio ranging from 4 to 20, which is a large range, the supershear transition distance never exceeds 4 times the seismogenic width, which is also not sensitive to the fault length. In another word, the supershear transition must occur shortly, or the restriction from the seismogenic width will make the transition impossible. And this observation is consistent with the Dunham 2007 paper, where he conducted fully dynamic simulations in 3D. We showed that our 2.5D model can actually produce similar behavior. Finally, we come back to the point and then ask why supershear are rare. Our work at least indicates that they are rare unconventional radiant state faults, given the parameters measured in the lab. First, our model requires a small A divided by B or a weak direct effect, while A and B's are typically shown to be more or less comparable in laboratory experiments. On the other hand, our model requires a large nucleation size. However, the typical nucleation length using parameters from the lab are on the order of meters or tens of meters, while the fault width is on the order of 5 to 10 kilometers, which is much larger than the fault nucleation length. Overall, we argue that the primary reason why supershear rarely occur is the low likelihood over multiple cycles of achieving sufficiently high initial stresses, either due to frequent earthquake nucleation or strong direct effect. Now, given the narrow parameter range where supershear can occur in our model, the question is then why supershears do occur in nature. On one hand, this could be due to the limitation of our current model as we use the radiant state friction for both nucleation and dynamic rupture. Real earthquakes normally experience dynamic weakening, which is not captured here. In the future, we would like to explore the effect of dynamic weakening, segmented and rough faults, and off-fault inelasticity. On the other hand, this brings up again the question Do large and small earthquakes nucleate in the same way or not? Small laboratory earthquakes may have different nucleation mechanism from the real and large earthquakes that occur in nature. With that, I would like to finish my talk. If you have any questions and suggestions, you're welcome to shoot me an email. I'd be very happy to hear from all of you. Thanks.